In previous lecture, we discussed one classic problem, that is Brachistochrone problem, that led to the growth of calculus of variation. Here we used Euler-Lagrange equation for deriving the governing differential equation to design a frictionless chute between 2 points in a vertical plane such that a body sliding under the action of its own weight, I mean through gravity, moves in the shortest interval of time. The variational method is used for continuous system to minimize the total potential energy, which results only governing differential equation by doing complex mathematics of calculus of variation. Of course, it gives the boundary condition also, but there exists another method, that is Rayleigh-Ritz method. What we do here, we choose a suitable shape function for the deformation of the system, then we minimize the total potential energy which led to the equilibrium configuration, and we can derive the critical load of the system. Let us discuss Rayleigh-Ritz method through an example. This is a fixed free column, and we will have to find the critical load of this column. Let us first assume the deflected curve of this member. Yes, this figure here, the height of the column is L. Let me this is the L, and let the deflected curve, we will use Rayleigh-Ritz method to solve the critical load of this column. Let the deflected shape deflected curve of the member is y is equal to a plus bx plus cx square. We assumed a quadratic function, and let us substitute the boundary condition. The first boundary condition is y is equal to 0 at x is equal to 0, which gives a is equal to 0. This is the one condition of this boundary condition which results the constant value. Another is at the fixed end the slope is equal to 0. So, we can write dy by dx is equal to b plus 2cx, and dy by dx is equal to 0 at x is equal to 0. Here, because this is x is equal to 0 and this is x is equal to L. So, this gives b is equal to 0. By using these two boundary conditions, we can find the constants which results, hence this y is equal to cx square. And this does not satisfy, one observation from here, this does not satisfy natural boundary condition of zero moment at free end. This is one observation. These natural boundary conditions, also known as forced boundary conditions, those force boundary conditions are shear force and bending moment, and essential boundary conditions are displacement conditions. There is the displacement as well as slope. Here the assumed deflected shape that got reduced to y is equal to cx square, and in Rayleigh-Ritz method next step is to find the total potential energy of the system. Then we will minimize the total potential energy from the principle of stationary potential energy. From that we can find the constant, assumed constant, which is left here in this expression y is equal to cx square, that is c. So let us first start for finding the potential energy. The total potential energy expression is, as usual, we have written this many times. So again I am writing 0 to L d square y by dx square whole square into dx minus p into integration 0 to L half into dy by dx whole square into dx. The first part is strain energy stored as bending energy, strain energy due to bending, and this is the external work done. And if we will substitute y is equal to cx square, this reduced to ei by 2 to integration 0 to L 4 c square dx minus p by 2 into integration 0 to L 4 c square into x square into dx, which results 2 ei into c square into L minus 2p c square LQ divided by 3. It is all right. Now, from principle of stationary potential energy, from principle of stationary potential energy, this is a principle of stationary potential energy, PSTP, principle of stationary total potential energy in fact. So, this is PSTP, and there the first variation of the total potential energy, this equal to 0. This implies d pi by dc is equal to 0, which implies if you differentiate this expression with respect to, this is pi, this is pi. If you differentiate this with respect to c, that will reduce to 4 ei into, with respect to c, if we differentiate, this becomes 4 ei into L into c minus 2 p LQ divided by 3 into 2c, this equal to 0, implies p is equal to 3 ei divided by L square. So, this is a approximate solution, this is approximate solution. The exact buckling load will be obtained if an infinite series is used for the assumed deflection. This is, you can write here, exact buckling load can be obtained if an infinite series is used for the assumed deflection, deflected shape. Let us write y is equal to cx square plus dx square. If we assume this, what the result we are getting, let us see. Then we will have to do dy by dx. This is 2cx plus 3dx square. If you write d square y by dx square, this becomes 2c plus 6dx. Here you will have to use d square by dx square as well as dy by dx for finding total potential energy. Because of that, we derived d square y by dx square and dy by dx. And if you substitute in the total potential energy expression, the total potential energy, this is phi. The expression once again I am writing here, Ei by 2 into integrating 0 to L d square y by dx square whole square into dx minus p into 0 to L half into dy by dx whole square into dx. If you substitute this thing here, Ei by 2 integration 0 to L, this if will be writing 4c square plus 24c dx plus 36 d square x square into dx minus p by 2 into integrating 0 to L 4c square x square plus 9 d square x to the power 4th plus 12 cd x cube. This multiply by dx. So, this is the total potential energy expression. If you simplify it, this becomes 2 Ei into L. If you integrate this and simplify, this becomes c square plus 3 cd L plus 3 d square L square minus p L cube by 30 multiplied by 20 c square plus 45 c d L plus 27 d square L square. So, this is the total potential energy. From principle of total potential energy, that is first variation of the total potential energy is equal to 0. From this you can write the partial differentiation of with respect to C is equal to 0 and del pi by del d is equal to 0. So, these two conditions that will be giving two equations. So, let us find it out. This del pi by del c, this equal to, if we will do, this is the pi value, this is the pi, this expression. So, if we will differentiate with respect to c, that will give 2 EI into L multiplied by 2C plus 3 DL minus PLQ by 30 by 40C plus 45 DL. So, this equal to 0, and if we will do partial differentiation with respect to D, this will give 2 EI L multiplied by 3 CL plus 6 D L square minus P L Q divided by 30 into 45 CL. CL you can write CL plus 40 plus it will be 54 D L square, this equal to 0. So, then we will have to solve this equation. We will have to solve this equation, two equations. Let us introduce the notation that alpha is equal to PL square divided by EI. Then if we will introduce this, these two equations that will reduce to in this format, you can do this small exercise, mathematical exercise. Here you will find I am directly writing 8 alpha multiplied by C plus L into 36 minus 9 alpha multiplied by D is equal to 0, and 20 minus 5 alpha multiplied by C plus L into 40 minus 6 alpha multiplied by D is equal to 0. So, in the matrix format you can write as 24 minus 8 alpha, this is 36 minus 9 alpha, this is 20 minus 5 alpha, this is 40 minus 6 alpha, this is the coefficient matrix, and this is the CD equal to 0. For trivial solution, this C and D is equal to 0, which gives the straight configuration of this fixed free column. So, that we are not interested for. We are interested for non-trivial solution. If non-trivial solution exists, then the characteristic equation can be obtained from the coefficient matrix by equating to 0. For non-trivial solution, you can write for non-trivial solution, this becomes coefficient matrix determinant of coefficient matrix is equal to 0. So, this is you can write as 24 minus 8 alpha, 36 minus 9 alpha, 20 minus 5 alpha, then 40 minus 6 alpha, that if you determinant this equal to 0. If implies, if you find the characteristic equation, that becomes 3 alpha square minus 104 alpha plus 240 is equal to 0. So, this is the characteristic equation. So, the roots of this characteristic equation are the eigenvalues. If we will back substitute in the equation, in the previous equation, previous governing equation, this equation, then we will get the eigenvector which gives the mode shape, buckling mode shape. So, if we will solve it, it will get the solution will be the smallest root, the smallest root is the critical load. This is the eigenvalue. This alpha is equal to 2.45, and you can write, we had assumed alpha as P L square by EI. So, you can write here this P L square by EI is equal to 2.45, implies P is equal to 2.45 EI by L square. So, the system is in equilibrium when this load P is 2.45 EI by L square. The system is equilibrium when it is applied with critical load. So, the column is equilibrium in bent up configuration means that time the applied load is critical load. So, here this whatever will P will get, that is the P critical. So, here the error is less than 1%. We can further reduce this error by considering more number of terms. Let us take an example where it is very much essential to consider more number of terms, else the result gives erroneous. So, if we will consider a column buckling problem with variable cross section, means the stiffness of this column along the length is different, then we will have to suitably choose the deflected shape, then only we will get the correct result.